I just want to do several examples now of implicit differentiation in applications, namely finding slopes of tangent lines, finding equations of tangent lines, and if we have time, even finding a second derivative. So, implicit differentiation examples. And so we'll start with the most basic type of question involving implicit differentiation, which might be find dy dx if, and I'll give you this implicit equation, let's say x over y equals x squared plus y squared, okay? And we want to find dy dx, which of course represents a formula for the slope of the tangent line. So here we have this implicit relationship between x and y, and we're going to differentiate both sides and solve for dy dx. So the first thing I'm going to do is take the derivative with respect to x of the left side and take the derivative with respect to x of the right side. So I've got d dx of, the left side is x over y, and on the right side I have d dx of x squared plus y squared. And now we're going to look at the differential equation that results and try to solve for dy dx. Now the left side is the derivative of a quotient of two functions of x. One of the functions is x itself, and the other is y, which is like f of x. And so we have to use the quotient rule. So we do the bottom, which is y, times the derivative of the top. The derivative of x is 1, so y times 1, minus the top, which is x, times the derivative of the bottom. The derivative of y is dy dx. Okay? So the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So we've got the derivative of the left side done. Now the right side's a bit easier. We can take the derivative of each summand independently. The derivative of x squared is just 2x. And the derivative of y squared is the power rule, so 2y to the first. But then since y is a function of x, we have to use the chain rule and multiply by the derivative of y, which is dy dx. And so now our goal is, with this mess, our goal is to figure out what a formula for dy dx. And so what we'll need to do here is get dy dx by itself on one side of this differential equation. And so the most natural thing I believe to do here is to clean up the left side by getting rid of the fraction. So let's multiply both sides by y squared. So if I do that, y squared is going to cancel on the left side. I suppose we could write it out. So I'll multiply the left side by y squared, and I'll multiply the right side by y squared. Okay? So on the right side it's going to distribute, and on the left side it's going to cancel with the division of y squared. So all we're left with on the left side is y times 1 is y, minus x times dy dx. And on the right side I have 2xy squared plus 2y to the third dy dx. Just distributing my y squared to both terms. Now if I want to get dy dx by itself, then I better get both terms that have dy dx involved on the same side of the equation. And so let's just say if I subtracted 2y cubed dy dx, I could do that. But then I'd have a negative x dy dx and a negative 2y cubed dy dx. We'd have both negatives, which is fine, but we try to avoid having more negatives than we need. So instead what I'll do is I'll add the x dy dx over here, and then I'll subtract the 2xy squared over there, so that the terms with dy dx are on the right side of the equation. So on the left side, I'll have my y. I'll leave him on the left because there's no dy dx. And I'll subtract 2xy squared from both sides, putting it over here and canceling it over here. And then on the right side, I'll have my 2y cubed dy dx. I want him to stay because he's got dy dx. And I need to add x dy dx to both sides. When I add it over here, it cancels. And when I add it over here, I just write it down. And now I've got all the terms with dy dx together, isolated on the same side. Everything without dy dx is on the left side. And what this does for us is it allows us to make sure that every term on the right side has a dy dx in common, which then permits us to factor out the common factor of dy dx. So if I factor out dy dx, again, take some notes for yourself about, I'm telling you the reasons we're doing these things, so if you're not comfortable with the algebra here, make some notes to yourself about why we're doing these things. Otherwise, it'll be meaningless when you look back at it later. So when we factor out, we're left with 2y cubed plus x. And finally, to get dy dx by itself, I can divide both sides by the factor of 2y cubed plus x to cancel on the right side and have it on the left side. So we see that dy dx ultimately ends up being y minus 2xy squared over 2y cubed plus x. And that's all we were asked to do in this problem. This is a formula that will allow us to find the slope of the tangent line to this original curve if we plug in an ordered pair x and y value, okay? We have time for a couple more examples here. All right. Let's see. Let's find the tangent line equation for the curve. The tangent line equation for the curve sine of x plus y equals 2x minus 2y at the ordered pair pi, comma, pi. Okay? So now we don't just want the tangent line slope, we want the tangent line equation. We want the y equals mx plus b equation of the tangent line, which of course we need the slope for, thus we need the derivative. We need dy dx from this equation. So let's differentiate both sides of the equation with respect to x. So d dx of the left side equals d dx of the right side. So on the left side, we've got the derivative of the sine of x plus y. And on the right side, we have the derivative of 2x minus 2y. So now we go through our implicit differentiation, understanding the difference between x and y. And so on the left side, we've got the derivative of a sine function, which is a cosine function. So the derivative of sine of x plus y is cosine of x plus y, but we have to implement the chain rule because the input here is more than just x. So we still have to multiply by the derivative of, let's write it out, the derivative of the inside, which is x plus y. Okay? So in the next step, we'll actually differentiate that sum. On the right side, the derivative of 2x is simple. That's just 2. Minus the derivative of 2y. Well, if this was x, the derivative would, if it was negative 2x, the derivative would be negative 2. But since it's negative 2y, the derivative is negative 2 times the derivative of y, which is dy dx. Again, that's the tricky part of implicit differentiation. Knowing the difference between differentiating x and y, okay? Okay, let's proceed. Let's go ahead and differentiate this guy now. We've got cosine of x plus y times the derivative of x is 1 plus the derivative of y is dy dx. And now, as before, we need to get all the terms with dy dx on the same side. Unfortunately, this dy dx is kind of buried within these parentheses. We need to get them out. So we're going to distribute our cosine of x plus y to both of those terms. So we get cosine of x plus y, when we multiply by 1, plus cosine of x plus y times dy dx for our second term. And now we've freed the dy dx from those that prison called parentheses, and just like last time, now we're going to get the two terms that have dy dx on the same side and everything else on the other side. So this is a negative 2 dy dx, so I'll put him over here to make him positive. So that'll give me cosine of x plus y times dy dx plus 2 dy dx. And on the right side, I'll have my 2 that I'm leaving there, and I'll subtract my cosine of x plus y, since it does not have a dy dx. And last, I'll factor out the dy dx. I'll factor out the dy dx on the left side, because both terms have that in common, leaving behind cosine of x plus y plus 2. And then finally, I'll divide by this sum to get dy dx by itself. So I'll just drop that off. I'm running out of space, so I'll just kind of make this short here. We'll just divide by that guy. And so this is dy dx. Now we have to use this to find the tangent line equation. Before I jump into the y equals mx plus b, I need to find the m part first. So the slope of that line is calculated using this formula by plugging in this x and this y. So on top I get 2 minus the cosine of pi plus pi. On bottom I get cosine of pi plus 2. So I get 2 minus, well, pi plus pi is 2 pi. And the cosine of 2 pi is 1, okay? So the cosine of 2 pi again is 1. And we can see that the slope is 2 minus 1 is 1, over 1 plus 2 is 3, so there our slope is 1/3. All right, so now we have the slope of the tangent line. And so what we'll do now is we've got our slope, we've got an x, and we've got a y. We've got a point and the slope. So let's use point-slope form to get the equation of the line. So we have y minus y1, the y value in the ordered pair is pi, equals m, 1/3, times the quantity x minus x sub 1, which is the x-coordinate here, which is also pi. And we're almost done. We just want the equation of our line to look like y equals mx plus b. So I'll distribute the 1/3 and add the pi. So I get 1/3 x, and I get minus pi over 3 when I distribute. So negative 1 pi over 3, and if I add pi, which is 3 pi over 3s, that gives me 2 pi over 3s. Okay? So the equation of the tangent line is y equals 1/3 x plus 2 pi over 3. Let me check how much time I have left here for this video and see if we have room for another example. Okay, we have time for another example. Let's do a second derivative. So we've done just a first derivative dy dx. We did the equation of a tangent line, which involved the slope of the tangent line. Let's do a second derivative. By the way, we also saw the quotient rule. You could certainly see the product rule. If you've got a product of functions, you could use any of the derivative rules that we've seen to do implicit differentiation. So if I want the second derivative, I could ask it a couple ways. I could say find y double prime, or I could say find d squared y dx squared, if I wanted Leibniz notation. Okay? This one is probably a little more natural if we're using Leibniz notation throughout our implicit differentiation anyway. But let's say that the implicit equation we're working with is x squared plus 4y squared equals 4. And so we would start by taking the derivative of both sides. So I'll do d dx of the left side, and I'll do d dx of the right side. So this gives me 2x, and then I do the derivative of 4y squared, which is just a power rule, telling me 8y to the first, but then I've got the chain rule because y is a function, so it's 8y times dy dx. And on the right side, the derivative of 4 is 0. And so we're asked to find y double prime, or the second derivative, basically. So let's get dy dx by itself. So I'll subtract 2x, giving me negative 2x, over 8y, which is negative x over 4y. Okay? Negative x over 4y. Now, if I want the second derivative, what I need to do is differentiate both sides again. So I'm going to take the derivative of the left side with respect to x. Make sure you get your notation right there. And I'll take the derivative of the right side with respect to x again. Thus, the left side turns into d squared y over dx squared. And yes, it seems like there should be parentheses around the dx, but the convention is to leave it off because it's not algebraically literally dx squared, it's the second derivative. So we'll keep the notation as short as possible. So what do we have on the right side? Well, we have a quotient. Let's go ahead and pull the coefficient of negative 1 to the front and ignore that as we do our quotient rule. So I've got the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 4 dy dx. Okay? All over the bottom squared. So if I multiply 4y times 4y, I get 16y squared. Now, we cannot stop here. When we're asked for the second derivative, the answer should not involve the first derivative. Okay? Well, it's okay to have it in terms of x and y, but we don't want it to involve a different derivative. So what we need to do now is replace dy dx with an expression involving x and y. And luckily, we know that dy dx from our previous work is negative x over 4y. So we will make that replacement. The second derivative equals negative fraction 4y minus x times 4 times the first derivative, which is negative x over 4y. All over 16y squared. Now we just clean it up. So much you could do here. We've got a negative fraction, 4y minus. This 4 cancels with the 4 in the denominator, and actually this negative times this negative makes this a positive. And then all that's left is x squared over y. X squared over y. Okay? All over 16y squared. And last, just because we don't like to leave messy complex fractions, if we can help it, we'll multiply the top and the bottom of this by y. And that's going to clear up that complex fraction. So the second derivative ends up being negative 4y squared plus the y's cancel, just leaving x squared, over 16y to the third. And that's an example of a second derivative using implicit differentiation.